Today we're going to look at a beginner sort of introduction to materials that we use in FRC, and also look at some of the kind of an introduction to the mechanical properties so we can talk about how the materials are different using some of the terminology, so we're all kind of talking about the same thing, because there's a lot of words that get thrown around when talking about materials, but if we're not all aware of those kind of same definitions, it's harder to discuss them and understand them in the same way. So let's go ahead and get started. First, we're going to look at the different types of mechanical properties. So one of the most crucial mechanical properties of the materials, and a lot of times, and it affects our choice quite a lot, is density. In FRC, we have a weight limit, right? The robot is only allowed to weigh so much. So it's important that if we're designing a part, and it has to be so big, there's a lot of times, right, the game pieces are so large or something, so the part needs to be a certain size to accommodate that, to accommodate whatever it's mounting to. If we were allowed to just have all the weight in the world and the weight didn't affect us in any way, we could use a lot of different materials that may have been heavier, but they'd be a lot stronger, and other types of the properties that we're going to look at here shortly. So without, but it's not just weight, right? The part weight is part of it, but the material property that we're looking at is called density. Ideally, you probably heard of this in either one of your science classes, chemistry, physics, something like that. For us, it's important when we're looking at how heavy something is, when we're choosing between different ways that we can make it. We could make it out of a metal, we could make it out of a plastic, we could make it out of all sorts of things. But if the part's going to kind of stay the same size, the part with the lower density is going to weigh less. The part with the higher density is going to weigh more. That's the old riddle is a really good example of kind of understanding density and understanding, kind of making sure you understand it intuitively. What's heavier, a pound of gold or a pound of feathers? If intuitively you think a pound of feathers is lighter, that's because you have this, like, the failure of understanding weight and density. If they both weigh a pound, they have to be the same. They have to be the same weight. There's going to be a lot more feathers, so the feathers are a lot less dense than gold is. And so it's especially difficult especially when we're talking about it normally, when we're talking about different parts and things, we'll often say plastic is lighter than metal, so we'll make it out of plastic or something like that. But it's not really lighter, it's just less dense. We're just not speaking as specifically as we probably should be in that context. Yeah, so the longer sentence would be, when we make this part out of plastic, it will be lighter than metal, and that's true. But the plastic itself is not necessarily lighter than metal. It's just less dense than the metal. Okay. Material strength, and we're also specifically talking about the strength of the properties of the material itself, not the shape that it's in. So we'll go over like how we can choose how to design things and the shape that we design things in, and some of the features we can use on the specific part to change things in another presentation. When we're talking about strength here, we're specifically talking about the strength of the material specifically, not the shape that we actually make it in and put it in to be on the robot. So the strength of the material is the ability to withstand a force. So either breaking or changing. So if we have a force trying to like pull a material apart, so if we take a specific size piece of metal or a specific size piece of plastic, and they're like the same size, and we apply the same, and we figure out how much force does it take to like rip apart that same size piece of metal compared to that same size piece of plastic. Generally speaking, the metal is going to be stronger, and it's going to take more force to rip it apart. Right? You should have some intuition on this. You've opened different things, used things in your life. Like, you kind of know, in general, something made of steel or another metal is going to be stronger than something made of most types of plastic. And so that force, the pulling apart force, is called tension. So the tensile strength of the material is how strong it is to resist being able to be ripped apart if you're pulling at two different ends. We have the opposite of that, which is how much force does it take to push the material together to form it and kind of change its shape when you squeeze it. So when you compress it together. So you can imagine like one of the big like car crushers when they're smashing a car together. There's different test units and things that are designed to test these material properties. So you can have, there's a machine that pulls things apart. There's another machine that'll just compress a column of a material and see what happens and how much force it can withstand when you push it together. You also have a bending force. So how easy it is it to bend the material if you have it loaded in this way, where you have it like supported on its two ends and you're pushing down in the middle. How easy is it for this whole piece to bend? So it's the bending strength of the material. A different property, but often related, and this is kind of why we're really talking about these first, is because they're very easy to get them to kind of talk about them all together, and they do overlap in some areas sometimes, so it's a little tricky to be to precisely talk about what the difference is between strength and toughness and some of the other things we're going to talk about as well. When we talk about a material's toughness, it's different than its strength. Its toughness is the way it reacts to a sudden impact. So it's often referred to as like impact resistance for tough materials. So basically, if you were to swing a hammer or an object at something, and if you had the same, most of the time when we're talking about this and we're comparing them, we're always going to be comparing across like the same size piece of material. So we would make little, like, if you were trying to like compare different ones, you would make test blanks where you'd have the same size piece of something. You'd be able to mount it in a similar way, and you'd be able to see which types of materials would take more energy to break in the toughness test, which one would take more force to break in the strength tests. So you can compare them to each other. So for a tough material, basically the way they kind of test it is you would have some sort of swinging object that's able to have a different amount of energy. So you could imagine you could bring it up to different heights that you were swinging to test if it would stay together when it was hit or if it would break. So maybe something that was not very tough, you could only bring it up to here, and when it swung down, it broke the piece. But something that was very tough, you'd be able to bring it all the way up to some much higher point. It would have a lot more energy as it swung down, just because gravity's making this go faster and faster as it comes in and it smacks it. And then eventually it would break, or maybe you have to build a different test jig because it's so tough that it won't break in the way that you're actually testing it. In general, you can think of rubber as like a very tough material, right? You can imagine how hard it would be to break rubber by smacking it with a hammer. It's probably not going to break no matter how hard you hit it, unless you have there's possibilities you can do different things to the rubber. We don't need to really get into it, but if you make it cold, things like that. But rubber in general is just a very, very tough material. Glass, on the other hand, you can imagine, be very easy to break with a hammer, where glass can also be very strong, though, right? It may be, you can imagine having a piece of glass that you could stand on, but at the same time, you wouldn't want to hit it with a hammer or stomp your feet on it or something, where you could think you would be able to break it because it's less tough, but it still may be strong in certain areas. Okay, I told you there was cookies involved. I wasn't lying. Brittleness versus ductility. Brittleness is how we describe how easy a material is to be fractured when it's subjected to a force or a load. So basically what we're looking at is when we actually when we do these tests, how does it break, not just when does it break. So if we if when you break the material, when you apply a force to the material, or if you're trying to like stretch the material, does it rip apart into pieces and they're kind of, everything kind of stays the same shape? There's just like a clean line down everything and it's just in two pieces. or does the material kind of stretch apart as it's going, and then eventually snaps apart, right? You can imagine pulling apart, say like a cookie. If you have a brittle original Chips Ahoy cookie, when you go to snap it, it sort of just snaps cleanly in half. If you have a chewy Chips Ahoy cookie, it's going to kind of fold, it's going to stretch a little bit, and then eventually you can get it to kind of rip apart, but it's not going to be in the same shape it kind of started in. The two halves, if you put them back together, the cookie's not going to be in the same shape because it's ductile and it changes shape, it elongates as you're going through that sort of bending or stretching, however you're deforming the cookie, the part, whatever it is. Often brittle materials will take more force to deform, so they'll basically be able to stay their same shape longer. But once they actually reach their breaking point, they're just going to snap. Where ductile materials may be able to stay together for a really long time, but they're going to be changing shape. And then sometimes they'll be able to, for some amount of that force, they may change shape. Then they'll be able to spring back if you let go. And at some point, if you keep pulling too hard and you start bending or changing its shape, it'll stay that way and it'll no longer come back. It won't like spring back to this original shape. So looking at this graph over here, we'll make it bigger on this next slide. You can see basically the y-axis is how much force you're applying, and the x-axis is kind of the change in shape. So in this kind of the graph up here, it's how far you're able to kind of stretch apart that material. How much longer it gets is the x-axis, and the y-axis is how much force it's taking. So a brittle material takes a lot of force without actually moving very much, so it's not able to be pulled apart at all. It's just sitting there, and you're pulling harder and harder, but it doesn't really move. And then eventually you reach some point where the material yields, which is where it breaks, and it rips apart kind of violently. This is if you were, if the times you've been trying to pull something apart or break something, and you get like pulled back because you're pulling so hard, and then you fall backwards or something because it didn't yield at all. It didn't or it didn't start stretching. It just all suddenly broke, all in one go. Where a ductile material will, at a much lower force, start getting longer and longer and longer, and then eventually, after basically you pull on it for a long time, you eventually can rip apart the whole thing, but it's going to be very long by the time you actually pull it all the way apart. Ductile materials are also normally able to be, you're able to change their shape, so you're able to like bend them intentionally and they'll stay together, able to form them into different shapes. So sometimes that can be a big advantage. Sometimes you want a brittle material that has this higher yield strength, this higher breaking strength, because that's what you're looking for, and that's how you need the part to behave. Okay. Hardness, and we get to another thing that a lot of times people, again, it's very easy to confuse these, where you're like, okay, is this thing tough or is it hard or is it strong? Like all of these words are often synonyms in normal language in some way. In material properties, they have a specific meaning. So hardness is the property that allows a material to resist sort of changes in a single spot. So it's if you can like push the material, and does it like allow it to give in a single spot? Can you scratch the material? Can you pull some of the material off of it? How easy is it to like, if you take your fingernail and scratch into it, does some of the material come off? Can you poke something through it? Any sort of small local deformation or breakaway of the material. So very hard materials in your head when you think about things that you've interacted with are diamond. So you have an idea of what diamonds are. They're very, very hard. That's why you may have heard of things called like diamond cutters and things, or like diamond coated saw blades, because diamond is a very hard material. So it's able to, when it goes through and tries to cut away at another material, the diamond won't get rubbed off. The diamond won't go away. The other material will Tungsten carbide is another type of very, very hard material that's used on cutting tools and things in the same way. You can get a tool that's coated in tungsten carbide or made out of tungsten carbide so that when it's cutting through um, another very hard material, it's able to cut through it, and the tool itself doesn't get cut, the material gets cut. Um, we also use hardness in a different way to describe um, types of rubbers. So a lot of times in an FRC, we have to be able to have like grippy material to be able to pick up objects or not have things slip around. Um, and those different rubbers have different hardnesses, and that's how we're able to kind of tell their difference. So a softer rubber will be more grippy, so it's able to like locally deform more, so it's easier to whatever the object is can kind of push into it harder, so it can push into it more, so it's less likely to slip around. And a harder rubber will be less grippy, so it's not going to if you put it on the table, it's going to be easier to like slide a harder rubber across the table than it is to slide a softer rubber. um, but the harder rubber, just like with the cutting tools like the diamond or the tungsten carbide, isn't going to have any of it it's going to be harder for it to have any bits of the rubber to kind of like peel off or break away. So this is what we call wear. So if the part starts wearing down, right, you can imagine if we use these wheels over enough time, the outside of them would eventually start getting smaller and smaller because bits of the rubber are going to peel off as we use them over and over again. And so the harder rubber, so the one with, in this case, the way we measure it is called durometer. An 80A is a much harder rubber on the outside of this wheel. So it's going to take longer for the wheel to basically become smaller and wear down. Or the much softer rubber, this 35A wheel, might start wearing down very quickly, and you'll notice that like the outside just won't be as clean and smooth, and it'll literally just start getting thinner and thinner as it gets used over and over again, and eventually we have to replace it more often because it just wears down um, to the point where it's no longer usable um, for any variety of reasons in that use case, right? It stops being able to grip the ball as well just because the rubber is completely gone or it's now a different size. So we'd have to change it out. And sometimes you also just want to test how they interact with different game pieces, because sometimes you may need, if something's too grippy, it won't actually suck it in as well. So there's different versions of it, and we can test how hard of a material we actually need to use on our rollers. Okay, so looking at some of the more specific materials, we can use some of those terms we just talked about to actually differentiate the different types of materials that we actually use on the robot. So steel is a very, very common material. You know what steel is, large parts of cars and buildings and many, many things are made of steel. Steel has a relatively high density. So a part made of steel compared to a part made of almost any other material we use, steel is going to be the heaviest choice if it's the same volume part, right? Steel is very strong and hard. Metals have some other properties in which they can be, not all steels are the same. They can have different heat treated levels, so you can do different things to them to, as you apply heat, their actual mechanical properties will change. You can also have different compositions. So steel isn't any one, but actually you produce steel, there's normally other metals and there's different alloys of iron and other things in it to make steel. And so the actual formula you have for that specific steel determines some of the properties. So some steels are more brittle than others. In general, steel is more brittle than some other metals. And because steel is hard and strong, it makes it somewhat difficult to machine. You can imagine if you were using a steel saw blade or a steel drill bit and you're trying to drill or cut through steel, you don't know necessarily which material is going to win in that case, right? So the drill bit may just be getting less sharp, or the saw blade may get less sharp as it's going through that also steel part. So that's where you often need things like a tungsten carbide cutter or other ways to make sure that the cutting tool that you're using is harder than the steel that you're cutting. So we don't really use we don't cut steel on like our CNC router or on our laser cutter or anything like that. We normally just use the other tools that we have in the lab to be able to cut through steel. Parts that need to be high strength and have really good wear properties. So just like we were talking about with rubber, because steel is really hard, it's very hard for bits of it to basically chip off in any way as it's getting used. So the parts will last a long time. They'll kind of stay in that same shape, even though it's being run over and over and over again. So we use steel a lot for gears and sprockets and relatively small parts where the increase in density to where they're heavier than the same part in aluminum, but because the part is relatively small, it doesn't affect our overall weight budget of the robot as much. So a lot of the gears and sprockets we'll use in the drivetrain where they're going to be run a lot. We never want to have a failure there. A lot of those parts will be steel most of the time. Steel is also a relatively cheap metal. It's produced in large quantities all over the world. So it's relatively easy to obtain and use, but it is more difficult to manufacture and for us to use as well. So we don't use it in a lot of things that we're making ourselves, but we will buy quite a few parts in, especially some of the smaller ones, in steel. Steel is also what most of our nuts and bolts are made out of. You can buy more expensive like aluminum nuts and bolts and you will save a little bit of weight because we'll talk about aluminum in a second. It's less dense than steel. But because the part is so small, it's rarely worth the having the not as strong material there. So almost all of our nuts and bolts are always steel. Aluminum. So aluminum is by far our most commonly used metal in terms of actually constructing the robot, the actual like frame and structural members of the robot. We use aluminum almost all the time for those parts if they're going to be metal. Aluminum is stronger than most plastics or wood. It's less dense than steel, so it's lighter if we're using the same size part. It is more expensive than steel, but it's still pretty reasonable, or at least it's most of the time more expensive than steel. And one of the most important properties of aluminum for our use cases is that it's in certain what are called alloys, which is the different chemical compositions that make up the types of aluminum. Aluminum can be very ductile, so it means it's able to be bent and formed into different shapes without cracking, right? So it's kind of like the Chewy Chip Ahoy, where we're able to sort of bend it and shape it into a shape that we want. It'll stay there, and so we can make more interesting shapes and things that way without having to cut out the entire shape or anything. Aluminum is softer than steel, so it's a lot easier for us to machine it. So we can use our CNC router very easily. Our sponsor can laser cut aluminum for us. Our sponsor can also laser cut steel for us in certain cases as well. And then it also cuts and drills relatively easily. So it's a lot easier to use our hand tools or our bench tools to add holes or cut parts and things as well. Okay, so steel and aluminum are by far the most common metals we'll use on the robot. There are some other ones that we'll go over in the future, and there may be some specific use cases for things like bronze. We've had titanium on the robot before, but most of the time there are disadvantages to those. So we won't use them unless there's a very specific reason why we need the properties of those metals. All right, so a couple of the plastics that we use. Actually, first, a plastic that we don't use. So this is probably one of the most useful things to understand that's not super common knowledge if you haven't been building robots or doing any other hobby specifically with plastic before, is the difference between acrylic or plexiglass. So these are the acrylic and plexiglass are the same thing. And the plastic we actually use called polycarbonate or Lexan that we're going to talk about on the next slide. So acrylic and plexiglass are very common. They're used in display cases and models and all sorts of different applications where you don't need them to be very tough at all, basically, right? They're not getting run into by anything. They're not taking any impacts. So acrylic and plexiglass work just fine for those applications. It's easy to obtain. You can get it at Home Depot or Lowe's or any of the big box stores. It's very inexpensive, and it does have its uses, and it's fine in those uses. Its uses just aren't on the robot. We'll very rarely even have any of it in the lab. We have a little bit. We normally will make trophies out of it sometimes because it's cheaper and you can get it in a variety of colors and you can make it. It's easy to route and laser cut and things like that. So we will use it for parts of our trophies that we'll make for some of the competitions we do. But we really won't ever have it on the robot as any sort of structural part of the robot, mostly because it is not tough and it breaks or cracks very easily when bent or struck. So it'll like snap if you try to bend it, which is actually one of the easiest way to test and kind of tell if something is acrylic or polycarbonate. It gets a little bit easier to tell, like it scratches a little bit differently. But it definitely takes a while to be able to just like instantly tell between acrylic and polycarbonate, and sometimes we will mess up. It's one of the reasons why we try not to keep much of it in the lab or have much of it at all, just because it's easy to think a clear sheet of plastic is polycarbonate, which is a great material, which we're going to talk about in just a second, when in reality it's acrylic. And if you were to make a robot part out of it, you may not notice until you go to actually run into something, or if you try to drill it or something else and it starts snapping and cracking, and then you have to start over with the polycarbonate part. So in general, just remember, we don't use acrylic or plexiglass, which are the same thing, on our robots. Okay, polycarbonate. So polycarbonate, also known as Lexan. The parentheses names are kind of the brand name. So I believe GE owns Lexan. There's other brand names for the same types of plastics, sometimes called Macrolon. Most of the time we'll call it polycarbonate. We'll shorten it to polycarb. But it's all roughly the same stuff. Polycarbonate is awesome. It's the same material used as bulletproof glass. Bulletproof glass is just a very thick version, often up to like an inch or 2 inches thick. But it's a really strong, tough plastic. And it also has a relatively high impact resistance. That's what that toughness means. So that when we run into things or if something hits it, it doesn't break or shatter or crack like acrylic would. Polycarbonate is also ductile, so that means we can bend it. So there are times that we'll bend it in the same way that we'll bend aluminum when we need to make different shapes and things out of it. We can put different angled bends directly in polycarbonate when it's thin. As you start getting thicker, any material is harder to bend for reasons we'll talk about a little bit later. It is less dense than aluminum, so it's lighter for the same part. So that's very convenient if we were making like the side of this intake out of aluminum and we had the same thickness, the aluminum part would be heavier. We use polycarbonate all over the robot. It's one of our kind of default go-to materials. If we can make it out of polycarbonate, we often will. It is more expensive than acrylic by quite a bit. It's cheaper than aluminum most of the time, especially for the same thickness. There are a lot of trade-offs we're not specifically going into, but a lot of times because like aluminum is a stronger material, you may be able to use a thinner aluminum than you would polycarbonate, and so the trade-offs get a little bit less easy to solve than we're kind of going over right now. They get more complicated, but in general, we use, if we can make something out of polycarb, we often will. One of the main reasons why we do that is it's very easy for us to machine polycarbonate. We can use our CNC router. We can use our laser cutter. It does leave a little bit of like a brownish yellow edge, which isn't exactly pretty, and it can be a little rough sometimes that you have to clean up, but it's still very fast for us to do that. We can, all of our saws and drills work just fine on it. And we have quite a bit of it. We stock quite a lot of it. So it's easy for us to have on hand and just kind of use as our default material. The 2020 intake. So this is the intake before we actually, we go through a process which we call frosting it, where we actually just like scratch up the entire outside of it to make it look more white instead of clear. The main reason we do that is just so if it starts eventually getting scratches on it, it doesn't look ugly. If we just scratch the entire surface immediately, it starts looking more, it doesn't matter if we scratch it later. It also matches our robot a little bit more because the rest of our robot's white as well. So these side panels were made out of polycarbonate. These are actually polycarbonate tubes that we actually used as the intake rollers. And they're designed that way so that if we run this part of the robot into something, so this is outside of our bumpers and this could actually hit another robot, it could hit field obstacles, these parts don't break since they're made out of polycarbonate, and they're able to be tough and they're able to bend a little bit if they need to without snapping or cracking. So these work well for that. The last type of plastic we're going to talk about today is called acetal or Delrin. It's more expensive than polycarbonate. That's the first thing. So we use it less often. It's less flexible than polycarbonate, but it has a higher bend strength. So basically, it'll stay a nice flat sheet under more bending load than a piece of polycarbonate will of the same thickness. It's a little bit more dense than polycarbonate, so it's slightly heavier. It's often sold in a white or black color or sheet, so it's easy for us to get white, so it matches the rest of our robot, which is another convenient reason for us. It's machined just like polycarbonate for the most part. It's pretty easy. And it has the advantage of having a much cleaner cut on the laser cutter. So if we need to do slightly more precise things like our gearbox plates, the Delrin is a little bit nicer there. We don't get any of those. We don't have to do any cleanup work, so you can keep the size of the holes the correct size the whole time very easily. And having these be less likely to have any of these plates bend or anything is also useful in this application. So that's one of the places we use it. We'll use it in a few other places. It's also a property we haven't talked about, but Delrin is a very slick material. It has a low amount of friction with other materials. So if something needs to slide on something else without having it roll or anything, if you just need it to slide back and forth, Delrin is very good for that. Yeah, so that's one of the use cases that we have for Delrin. There's a few others that will make things out of Delrin when we want something that isn't as easy to bend as polycarbonate is. Okay. wood is the last material we're going to talk about, and we're going to talk about it pretty generally. A lot of people wouldn't think that we would use wood on a robot ever, and a lot of teams don't. But there are some really good advantages to using wood, and there's times where we will use it on our robots. So wood in general is less dense than polycarbonate and other plastics, and it's a lot less dense than aluminum and other metals. It is brittle. It'll snap. So if you go to just like, you've taken any sort of wood thing before and bend it and break it, it's not going to stretch at all or anything, right? Wood doesn't. It's not easy to bend or stretch or anything like that. It's a very brittle material. It's a very soft material, so it's really easy to route, laser cut, drill, saw, all of that. Super easy to machine and work with. In general, it's very inexpensive for the types of wood that we're using. You can get really expensive wood. They're very wood that's less common, things like that. They get more expensive. But for most of the wood we're using, we can get it very inexpensive for the amount of wood that we can get with it. So we use it, especially some of the cheaper varieties that we can pick up. You can use it for prototypes and things that we know are going to be replaced really quickly. So there's often parts that we just need to be able to test the fit and form and function of, like the version of the intake before we had our final version. So these plates are made of just inexpensive plywood that we can run through the laser cutter very fast. They were never going to plan to stay on the robot. So they were probably on the robot for less than a week total. Right, a version of them might have been on there for less than a day, because this is also where we figure out if there's any errors. So maybe we had something in the CAD wasn't quite right and a mounting hole was wrong or something, and we just need to immediately, right after trying to put it on, we realize it doesn't work. We immediately cut new ones, and it's totally fine to just either throw this in the scrap pile or throw it away, because this piece of wood just doesn't cost us very much money, so we're not too worried about it. Wood's also more environmentally friendly. It'll biodegrade, that sort of thing too. So it's nice if we're gonna have a lot of trash. It's better if it's wood than if it's plastic or something else that is something that can't be recycled as easily. Different types of wood have dramatically different properties. So most of the time, if we're gonna keep, if the wood's actually gonna be a final part of our robot, which it often is, we'll use what's called Baltic birch plywood, and it's a very specific way that they make the plywood, where it's made from sheets of birch wood, and each ply is just solid birch all the way through. It is more expensive, but it allows it to be far stronger, and it's really good in bending strength. So we'll use it as the belly pan of our robot, the part that kind of connects the frame and where we mount a lot of electronics to, because it's very low density and it allows the whole frame to be very rigid, since the wood doesn't want to bend at all. In 2020, we actually used it here. So this piece of wood that you see on the robot actually did stay wood. We ended up covering it with a very thin sheet of plastic so the balls would want to slip across it. But the actual part stayed wood on our competition robot because it didn't need to be impact resistant. It was inside the robot. Nothing else was going to hit it in here. It was a rather large flat piece of material. So if we used the same part in plastic or aluminum, it was going to be heavier. Or if we tried to make it lighter by making the part a thinner piece of plastic or aluminum, it might start bending or sagging in the middle, and we didn't want that to happen. So taking the advantages and using the advantages of the wood allowed us to get the properties we wanted in the specific area of the robot. Okay, so that was the last slide I had. Some of the key takeaways that we already kind of talked about, but just make sure you sort of remember. Density is mass per volume. So it's how heavy something is compared to its size, right? So, and we can look at the different, generally, metals have a higher density than plastics than does wood. Brittle materials break or crack instead of stretch or bend. Should be pretty easy to remember that brittle is kind of the regular Chips Ahoy, ductile are the chewy. Harder rubbers are less grippy and last longer. Softer rubbers are more grippy and wear faster. Steel is more dense and stronger than aluminum. Aluminum is used because it is of its ductility, so it's able to be bent, and it's lower density, and it's easier to machine. So it's easier for us to make parts out of aluminum than it is to make parts out of steel. Very important to never use acrylic on the robot. We also use polycarbonate a lot on the robot because it is tough and it's less dense than aluminum. And then wood can be strong and has a low density. So there's very specific use cases we use on the robot, but it's not something that we don't default to just making things out of wood on the actual competition robot.